Nitrogen is a chemical element with symbol N and atomic number 7. It is the lightest nitrogen, and at room temperature, it is a transparent, odorless diatomic gas. Nitrogen is a common element in the universe, estimated at about 7th in total abundance in the Milky Way and the Solar System. On Earth, the element forms about 78% of Earth's atmosphere and as such is the most abundant uncombined element. The element nitrogen was discovered as a separable component of air by Scottish physician Daniel Rutherford in 1772. Many industrially important compounds, such as ammonia, nitric acid, organic nitrates, and cyanides, contain nitrogen. The extremely strong triple bond in elemental nitrogen dominates nitrogen chemistry, causing difficulty for both organisms and industry in converting the N2 into useful compounds, but at the same time causing release of large amounts of often useful energy when the compounds burn, explode, or decay back into nitrogen gas. Synthetically produced ammonia and nitrates are key industrial fertilizers, and fertilizer nitrates are key pollutants in causing the eutrophication of water systems. Outside the major uses of nitrogen compounds as fertilizers and energy stores, nitrogen is a constituent of organic compounds as diverse as Kevlar fabric and cyanoacrylate, super glue. Nitrogen is a constituent of molecules in every major pharmacological drug class, including antibiotics. Many drugs are mimics or prodrugs of natural nitrogen-containing signal molecules. For example, the organic nitrates nitroglycerin and nitroprusside control blood pressure by being metabolized to nitric oxide. Plant alkaloids contain nitrogen by definition, and thus many notable nitrogen-containing drugs, such as caffeine and morphine, are either alkaloids or synthetic mimics that act on receptors of animal neurotransmitters. Nitrogen occurs in all organisms, primarily in amino acids, in the nucleic acids and in the energy transfer molecule adenosine triphosphate. The human body contains about 3% by mass of nitrogen, the fourth most abundant element in the body after oxygen, carbon, and hydrogen. The nitrogen cycle describes movement of the element from the air into the biosphere and organic compounds, then back into the atmosphere. History and etymology. Nitrogen is formally considered to have been discovered by Scottish physician Daniel Rutherford in 1772, who called it noxious air. Though he did not recognize it as an entirely different chemical substance, he clearly distinguished it from Joseph Black's fixed air, or carbon dioxide. The fact that there was a component of air that does not support combustion was clear to Rutherford. Nitrogen was also studied at about the same time by Carl Wilhelm Scheele, Henry Cavendish, and Joseph Priestley, who referred to it as burnt air or phlogisticated air. Nitrogen gas was inert enough that Antoine Lavoisier referred to it as mephitic air, or isoter, from the Greek words eta omega tau omicron sigma azotos, lifeless. In it, animals died and flames were extinguished. This mephitic air consisted mostly of N2, but might also have included more than 1% argon. Lavoisier's name for nitrogen is used in many languages and still remains in English in the common names of many compounds, such as hydrazine and compounds of the azide ion. The English word nitrogen entered the language from the French nitrogène, coined in 1790 by French chemist Jean-Antoine Chaptal, from the Greek nu iota tau rho omicron nu nitron, sodium carbonate, and the French gene, producing, from Greek gamma epsilon nu eta sigma genes, producer, begetter. The gas had been found in nitric acid. Chaptal's meaning was that nitrogen gas is the essential part of nitric acid, in turn formed from saltpeter, then known as niter. Nitrogen compounds were well known by the Middle Ages. Alchemists knew nitric acid as aquafortis. The mixture of nitric and hydrochloric acids was known as aqua regia, celebrated for its ability to dissolve gold. The earliest military, industrial, and agricultural applications of nitrogen compounds use saltpeter, most notably in gunpowder, and later as fertilizer. In 1910, Lord Rayleigh discovered that an electrical discharge in nitrogen gas produced active nitrogen, a monatomic allotrope of nitrogen. The whirling cloud of brilliant yellow light produced by his apparatus reacted with quicksilver to produce explosive mercury nitride. For a long time, sources of nitrogen compounds were limited. Natural sources originated either from biology or deposits of nitrates produced by atmospheric reactions. Nitrogen fixation by industrial processes like the Frank-Caro process and Haber-Bosch process eased this shortage of nitrogen compounds, to the extent that half of global food production now relies on synthetic nitrogen fertilizers. At the same time, use of the Ostwald process to produce nitrates from industrial nitrogen fixation allowed the large-scale industrial production of nitrates as feedstock in the manufacture of explosives in the world wars of the 20th century. Production. Nitrogen gas is an industrial gas produced by the fractional distillation of liquid air, or by mechanical means using gaseous air. Commercial nitrogen is often a byproduct of air processing for industrial concentration of oxygen for steelmaking and other purposes. When supplied compressed in cylinders, it is often called OFN. In a chemical laboratory, it is prepared by treating an aqueous solution of ammonium chloride with sodium nitrite, NH4Cl plus nano2N2 plus NaCl plus 2H2O. Small amounts of impurities NO and HNO3 are also formed in this reaction. The impurities can be removed by passing the gas through aqueous sulfuric acid containing potassium dichromate. Very pure nitrogen can be prepared by the thermal decomposition of barium azide or sodium azide. 2Nan3 plus 3N2 properties. Nitrogen is a nonmetal, with an electronegativity of 3.04. It has 5 electrons in its outer shell and is, therefore, trivalent in most compounds. The triple bond in molecular nitrogen is one of the strongest. The resulting difficulty of converting N2 into other compounds, and the ease of converting nitrogen compounds into elemental N2, have dominated the role of nitrogen in both nature and human economic activities. At atmospheric pressure, molecular nitrogen condenses at 77 K and freezes at 63 K into the beta-hexagonal close-packed crystal allotropic form. Below 35.4 K, nitrogen assumes the cubic crystal allotropic form. Liquid nitrogen, a fluid resembling water in appearance, but with 80.8% of the density, is a common cryogen. Unstable allotropes of nitrogen consisting of more than 2 nitrogen atoms have been produced in the laboratory, like N3 and N4, under extremely high pressures and high temperatures, as produced using a diamond anvil cell. Nitrogen polymerizes into the single-bonded cubic gauche crystal structure. This structure is similar to that of diamond, and both have extremely strong covalent bonds. N4 is nicknamed nitrogen diamond. Other allotropes include hexazine and octarazicubane. The former is predicted to be highly unstable, while the latter is predicted to be kinetically stable, for reasons of orbital symmetry. Isotopes. There are 2 stable isotopes of nitrogen, 14N and 15N. By far the most common is 14N, which is produced in the CNO cycle in stars. Of the 10 isotopes produced synthetically, 13N has a half-life of 10 minutes and the remaining isotopes have half-lives on the order of seconds or less. Biologically mediated reactions strongly control nitrogen dynamics in the soil. These reactions typically result in 15N enrichment of the substrate and depletion of the product. A small part of the molecular nitrogen in Earth's atmosphere is the isotopal log 14N15N, and almost all the rest is 14N2. The radioisotope 16N is the dominant radionuclide in the coolant of pressurized water reactors or boiling water reactors during normal operation. It is produced from 16O via reaction. It has a short half-life of about 7.1 s, but during its decay back to 16O, produces high-energy gamma radiation. Because of this, the access to the primary coolant piping in a pressurized water reactor must be restricted during reactor power operation. 16N is one of the main means used to immediately detect even small leaks from the primary coolant to the secondary steam cycle. In similar fashion, access to any of the steam cycle components in a boiling water reactor nuclear power plant must be restricted during operation. Condensate from the condenser is typically retained for 10 minutes to allow for decay of the 16N. This eliminates the need to shield and restrict access to any of the feed water piping or pumps. Electromagnetic spectrum. Molecular nitrogen is largely transparent to infrared and visible radiation because it is a homonuclear molecule and, thus, has no dipole moment to couple to electromagnetic radiation at these wavelengths. Significant absorption occurs at extreme ultraviolet wavelengths, beginning around 100 nanometers. This is associated with electronic transitions in the molecule to states in which charge is not distributed evenly between nitrogen atoms. Nitrogen absorption leads to significant absorption of ultraviolet radiation in the Earth's upper atmosphere and the atmospheres of other planetary bodies. For similar reasons, pure molecular nitrogen lasers typically emit light in the ultraviolet range. Nitrogen also makes a contribution to visible air glow from the Earth's upper atmosphere, through electron impact excitation followed by emission. This visible blue air glow typically results not from molecular nitrogen but rather from free nitrogen atoms combining with oxygen to form nitric oxide. Nitrogen gas also exhibits scintillation reactions in general. Nitrogen is unreactive at standard temperature and pressure. N2 reacts spontaneously with few reagents, being resilient to acids and bases as well as oxidants and most reductants. When nitrogen reacts spontaneously with a reagent, the net transformation is often called nitrogen fixation. Nitrogen reacts with elemental lithium. Lithium burns in an atmosphere of N2 to give lithium nitride. 6 Li plus N2 2 Li 3N. Magnesium also burns in nitrogen, forming magnesium nitride. 3 megagrams plus N2 Mg3N2N2 forms a variety of adducts with transition metals. The first example of a dinitrogen complex is Ru5 2+. However, it is interesting to note that the N2 ligand was obtained by the decomposition of hydrazine, and not coordination of free dinitrogen. Such compounds are now numerous. Other examples include IRCl2, W22, and 2ZR2. These complexes illustrate how N2 might bind to the metal in nitrogenase and the catalyst for the Haber process, a catalytic process to reduce N2 to ammonia with the use of a molybdenum complex in the presence of a proton source, was published in 2005. The beginning point for industrial production of nitrogen compounds is the Haber process, in which nitrogen is fixed by reacting N2 and H2 over an iron oxide catalyst at about 500 degrees Celsius and 200 atmospheres pressure. Biological nitrogen fixation in free-living cyanobacteria and in the root nodules of plants also produces ammonia from molecular nitrogen. The reaction, which is the source of the bulk of nitrogen in the biosphere, is catalyzed by the nitrogenase enzyme complex that contains FeNO atoms. Using energy derived from hydrolysis of adenosine triphosphate into adenosine diphosphate, an inorganic phosphate occurrence. Nitrogen gas is the largest constituent of Earth's atmosphere. However, this high concentration does not reflect nitrogen's overall low abundance in the makeup of the Earth, from which most of the element escaped by solar evaporation, early in the planet's formation. Nitrogen is a common element in the universe. and is estimated to be approximately the seventh most abundant chemical element by mass in the universe, the Milky Way, and the Solar System. In these places it was originally created by fusion processes from carbon and hydrogen in supernovas. Molecular nitrogen and nitrogen compounds have been detected in interstellar space by astronomers using the Far Ultraviolet Spectroscopic Explorer. Due to the volatility of elemental nitrogen and also its common compounds with hydrogen and oxygen, nitrogen and its compounds were driven out of the planetesimals in the early solar system by the heat of the sun, and in the form of gases, were lost to the rocky planets of the inner solar system. Nitrogen is therefore a relatively rare element on these inner planets, including Earth as a whole. In this, nitrogen resembles neon, which has a similar high abundance in the universe, but is also rare in the inner solar system. Nitrogen is estimated at 31st element in crustal abundance. There exist some relatively uncommon nitrogen minerals, such as saltpeter, Chile saltpeter, and sal ammoniac. Even these are known mainly as concentrated from evaporative ocean beds. Due to their ready solubility of most naturally occurring nitrogen compounds in water, a similar pattern occurs with the water solubility of the uncommon light element boron. However, nitrogen and its compounds occur far more commonly as gases in the atmospheres of planets and moons that are large enough to have atmospheres. For example, molecular nitrogen is a major constituent of not only Earth's atmosphere, but also the Saturnian moon Titan's thick atmosphere. Also, due to retention by gravity at colder temperatures, nitrogen and its compounds occur in trace to appreciable amounts in planetary atmospheres of the gas giant planets. Nitrogen is present in all known living organisms, in proteins, nucleic acids, and other molecules. It typically makes up around 4% of the dry weight of plant matter, and around 3% of the weight of the human body. It is a large component of animal waste, usually in the form of urea, uric acid, ammonium compounds, and derivatives of these nitrogenous products, which are essential nutrients for all plants that cannot fix atmospheric nitrogen compounds. The main neutral hydride of nitrogen is ammonia, although hydrazine is also commonly used. Ammonia is more basic than water by 6 orders of magnitude. In solution, ammonia forms the ammonium ion. Liquid ammonia is amphiprotic and forms ammonium and the less common amide ions. Both amides and nitride salts are known. Many of them decompose in water, but there are exceptions like gallium nitride or boron nitride that have strong polar covalent network structures. Singly, doubly, triply and quadruply substituted alkyl compounds of ammonia are called amines. Larger chains, rings and structures of nitrogen hydrides are also known, but are generally unstable. Other classes of nitrogen anions are the poisonous azides, which are linear and isoelectronic to carbon dioxide, but which bind to important iron-containing enzymes in the body in a manner more resembling cyanide. Another molecule of the same structure is the colorless and relatively inert anesthetic gas nitrous oxide, also known as laughing gas. This is one of a variety of nitrogen oxides that form a family often abbreviated as NOx. Nitric oxide is a natural free radical used in signal transduction in both plants and animals, for example, in vasodilation by causing the smooth muscle of blood vessels to relax. The reddish and poisonous nitrogen dioxide number 2 contains an unpaired electron and is an important component of smog. Nitrogen molecules containing unpaired electrons show a tendency to dimerize, and are, in general, highly reactive. The corresponding acids are nitrous HNO2 and nitric acid HNO3, with the corresponding salts called nitrites and nitrates. The higher oxides dinitrogen trioxide N2O3, dinitrogen tetroxide N2O4 and dinitrogen pentoxide N2O5 are unstable and explosive, a consequence of the chemical stability of N2. Nearly every hypergolic rocket engine uses N2O4 as the oxidizer. The fuels, various forms of hydrazine, are also nitrogen compounds. These engines are extensively used on spacecraft such as the Space Shuttle and those of the Apollo program because their propellants are liquids at room temperature and ignition occurs on contact without an ignition system, allowing many precisely controlled burns. Some launch vehicles such as the Titan II and Ariane 1 through 4 also use hypergolic fuels, although the trend is away from such engines for cost and safety reasons. N2O4 is an intermediate in the manufacture of nitric acid HNO3, a strong acid and a fairly strong oxidizing agent. Nitrogen is notable for the range of explosively unstable compounds that it can produce. Nitrogen triiodide Ni3 is an extremely sensitive contact explosive. Nitrocellulose, produced by nitration of cellulose with nitric acid, is also known as gun cotton. Nitroglycerin, made by nitration of glycerin, is the dangerously unstable explosive ingredient of dynamite. The comparatively stable, but less powerful explosive trinitrotoluene is the standard explosive against which the power of nuclear explosions are measured. Nitrogen can also be found in many organic compounds. Common nitrogen functional groups include amines, amides, nitro groups, imines, and enamines. The amount of nitrogen in a chemical substance can be determined by the Kjeldahl method.